Welcome, Professor Adam Riess, Nobel Prize in Physics and distinguished professor at Johns Hopkins University, and also to Antonaldo Diaferio, President of Infinito, the Planetarium of Torino, and the Museum of Astronomy and Space Attilio Ferrari. We are here for this interview on occasion of the Astronomy Day 2024. The title is 100 extragalactic years. So I led the word to Professor Diaferio to explain our meeting and interview.
Well, thank you, Gabriele. So the reason why we call this Astronomy Day the 100 years extragalactic years is that we need a prologue for this, right? Because in 1912, Henrietta Leavitt at the Harvard College Observatory, using photographic plates of the small Magellanic Cloud, investigated the properties of the Cepheids, which is a class of stars whose luminosity varies periodically. And she discovered a fundamental relation between the period over which the luminosity of a Cepheid varies and its luminosity. And this discovery was revolutionary because it provided a unique and most powerful tool at that time to measure cosmic distance. So why this is important is because in January 1925, so 13 years later, using this discovery by Henrietta Leavitt, Edwin Hubble published a paper where he demonstrated that the Andromeda Nebula, that now we call the Andromeda Galaxy, was an object at an enormous distance, well beyond the borders of our Milky Way. In other words, he discovered that Andromeda was an extragalactic object. And this was the first object known to humankind to be extragalactic. And so, in a way, 100 years ago, extragalactic astronomy was born. So this is why we want to celebrate this event with the Astronomy Day, and that's why we call it the 100 extragalactic years. And indeed, in these last 100 extragalactic years, our understanding of the universe and especially its content deeply changed. And the most astonishing discovery already occurred a few years later in 1929, again by Hubble, who showed that the universe is currently expanding. But another impressive discovery appeared in 1988 by Professor Adam Riess and collaborators. They discovered that the expansion of the universe is actually accelerating nowadays. And so they open up a number of questions about fundamental physics, and we still lack a definite answer to the question, why is universe expansion accelerating? And this is a very stimulating question, but especially stimulating question for fundamental physics. And on top of this, many other issues actually popped up, but that it's probably, the good starting point for asking Adam Riess his opinion on all these issues.
So thank you, Professor Diaferio. So I'll start with a short list of questions to Professor Riess, trying to shed some light about his fascinating studies. I would like to start, Professor, asking you about the discovery of your team about the expansion of the universe, and this expansion, according to your studies, is speeding up. And instead of slowing to a halt and collapsing, the universe apparently will expand until it's cold and dark, so fueled by a, let's say, mysterious dark energy. So the question is, what will be the final outcome of the universe?
Yeah, well, that's a good question. And of course, nobody will be around to tell us or check on us. And as we often note in astronomy, the sun will swell up as a red giant and engulf the Earth long before that. But nevertheless, for the rest of the universe, so if it's the most, I'll say, simple interpretation of what we've seen, then it would suggest that something that Einstein had first suggested, that there's something called a cosmological constant, or today physicists would say that there's a background energy, and that is going to continue to accelerate the expansion of the universe, so that in the future, everything will be very far apart from everything else. We won't be able to see anything except for the few galaxies that are gravitationally stuck to us, essentially. And then eventually, in time, most of the sources of energy will run out from stars. Things will be largely converted into black holes. And so it's going to be very sort of quiet, chilly end to the universe. But it's also important to note that we don't really understand yet this phenomenon of the accelerating expansion. So there are other possibilities which are less simple, which actually can change the story, even allowing the universe to recollapse in the future. So this is still something that's um, an area of research.
Okay, so it's an open story,
Mhm.
and so very fascinating. Um, let's focus for a moment on dark energy, since dark energy, let's say, has prompted an outpouring of papers and speculations. So we know that it's possible that dark energy constitutes some about three-quarters of the weight of the universe. So can you just help us to understand what it is, dark energy, where does it come from, and if it's forever or not?
Yeah, well, so this is exactly the questions that scientists more broadly have about it. So there are a number of new space missions which have been launched or are being launched in the coming years to study this question. There are technical ways we can try to answer those questions by making more detailed measurements. But really, the question is, where did it come from? Physicists don't really know. How long will it last? Is it constant? Will it change in time? We don't know that either. About all we know is that in Einstein's theory of general relativity, that dark energy is something that would accelerate the expansion of the universe, which of course is what we see, and that in some ways it's kind of natural. We even think this might be the second episode when something like this has occurred, that a previous episode may have occurred shortly after the Big Bang, a period that cosmologists call inflation, which would have operated by a similar mechanism. So mostly we have questions, but it's not pure speculation. We see many clues that tell us that there is dark energy. We just have still struggled to understand in detail how it works.
And Professor, you use the Hubble Space Telescope to find distant supernovae, and you detected an earlier era when the universe was slowing down before dark energy began to dominate and made the expansion speed up. So, which are the consequences of this discovery on our understanding of fundamental physics?
Um, well, these pieces of research and others, investigations of the cosmic microwave background after the Big Bang, have sort of, I would say, confirmed and solidified our view that dark energy exists. So it's gone from something that was either speculative or only hinted at by data to something that's kind of in the mainstream of cosmology. But it's also crystallized these questions about the things we don't understand about it. And so this has motivated a new generation of facilities to study the phenomenon. And we're hoping to get some answers in the next, oh, I would say 5 years or so, as these surveys do their work and give us initial information.
Okay, and since we talked of the discovery made through possible by the Hubble Space Telescope, we know that now we have the James Webb Telescope in the space, and I would like to ask you which can be the role of this telescope in the most areas of the universe
Right.
and what we can get from it.
It's a good question. Telescopes, they're a little bit like, I don't know, if you use an analogy, tools that doctors use. Sometimes they use a scalpel, Sometimes they use, lasers, or they, might use, other different kind of tools depending on the purpose. And so in astronomy, these telescopes uh, all have very different capabilities. And in the case of dark energy, it's such a subtle effect, and it operates uh, across the universe that we need to observe large fractions of the sky to be able to kind of tease out its effects. And so while Hubble and James Webb help and have helped in some specific cases, a lot of our sort of hopes and dreams about learning about dark energy are really coming from a new generation of wide field survey instruments. The European Space Agency recently launched Euclid for this purpose, and NASA is due to launch the Roman Space Telescope in about a year and a half. So it's that generation of facilities which are dedicated to the study of dark energy that are most likely to be productive.
Okay. And let's go back for a moment to the expansion of the universe. Uh, you are uh, you're focusing on the measures of the Hubble-Lemaitre constant and on its further and possible implications on our understanding of the physical world. So, are you now expecting some new and extraordinary discoveries by these studies?
Right. I mean, I don't know about the expectation side, but on the measurement side, this is sort of what scientists do is, we have some new model or new understanding of the universe, and then we say, okay, let's do a further experiment to see if that new model or understanding works or explains the universe in many different ways that we can look at it. And so my colleagues and I have been focusing on measuring the present expansion rate of the universe, as you said, the Hubble-Lemaitre constant, and comparing that to the predicted value today based on the new standard model of the universe, which includes dark energy, it includes dark matter, and it's calibrated by radiation left over from the Big Bang. And what we're seeing is that they don't match, that the prediction does not match the observation. And again, it's subtle. It's something that required much more precise measurements to determine. And right now, we don't know why. We don't know if part of the reason is because dark energy is more complicated, that it's not the simplest form that Einstein would have predicted, or if there's something else in the universe going on. We're looking for errors in the measurements, but it's been a decade of looking for errors, and nobody has found one that appears significant. So, this is very much a story to determine maybe when we come back on the 200-year anniversary of extragalactic astronomy, we'll have answers to those things. But right now we don't.
Okay, so Professor, I have a final question, especially for our audience. Can you explain to us how an astrophysicist works in his lab? I mean, how do you combine uh, diverse elements such as high tech,
Mm.
theory, math, and your personal creativity? We are very
Yes,
curious to know about
right.
how the mind scientists work.
Yes, it's a great question. So different astronomers do this differently. Anything from having a laboratory where they are building components or maybe a whole telescope to those who have very pristine offices because they only have pencil and paper and they're writing equations. And I'm in a different category where I'm a heavy user of these state-of-the-art telescopes, but they're space telescopes. So I didn't build any of them in my laboratory. Rather, they were built by space agencies and launched, and then people like me propose to use them and use them. And then we do a lot of data crunching. So we have a lot of first there's rounds of setting instructions to the space telescope. So you'll see us coding and calculating what kind of exposure times we need and which filters we need and where we want to observe. And it's very sophisticated in that we really model what we expect to see and what it would take to see that, and then give those instructions to the telescope. And then we wait. It could be hours, weeks, months, years, depending on what's most efficient for the scheduling of the telescope, before we learn observations have been obtained, and then they're beamed back to us over the internet. And then begins a new round of calculating and measuring. And it's a process of taking a huge set of numbers and hopefully getting down to a simple answer like yes or no or a number. And that process is called data reduction, because we literally go from huge piles of numbers to hopefully something simple. And so that's what we do. So some days we're going over those calculations. Other days we're giving presentations to each other about those calculations, or we're writing up detailed descriptions of what we've done and producing papers. And then sometimes we give interviews to the public to tell them, what this is all about. So it's very interdisciplinary in that sense. But it's fun, and I find it very entertaining. And of course, there's teaching as well, as most university professors do. That's all sort of part of the part of the day.
So, Professor, you are talking about the data reduction of time, but I'm sure that Professor some curiosities, and I can give him some closing remarks for closing our extraordinary interview.
Yes. Thank you. Thank you, Gabriele. Yeah, Adam Riess gave a very nice picture of what scientists really do. It's a very diverse activity, and you never get bored when you work in science, right? As Adam actually very well depicted. So, well, I wish to thank Gabriele Beccaria for asking these very, precise and interesting questions, and especially many thanks to Professor Adam Riess for his time and for his very well, organized answers and very comprehensive answer, and hopefully, these topics are of interest for our audience, and I'm sure that on November 15th, when we will have the public lecture by Professor Adam Riess to a larger audience, then people will be interested to listen to his lecture and in his answer to the question directly from the public. So thank you to both of you for your time and for your effort. And thank you also for the people that will be listening to this interview. Thank you very much.
Thank you.